Hello, it's Keith here, and this is lesson 5 of the Photon series of my 650 assembly programming tutorials. What's Photon? Well, it's my little Tron clone. You can see it loading up here. So this is Photon, and basically it becomes a tutorial series on how to do pixel plotting and pixel reading from the screen. So it's this little game here. Now, the game has a couple of elements we'll just want to discuss so that we understand the code. Firstly, if I hold down fire, then I will actually move faster. And this is to allow me to sort of catch up with the enemy. And also if I press a direction and hold it, I'm holding the direction now, but I've only turned once. Actually, it looks like the game's a little bit slow here. Maybe I need to change the speed settings a bit. Anyway, we're going to look at the source code today, and we're going to learn how the game works. Okay, well, let's go over to the source code and let's take a look. Okay, so here's the code, and first of all, I'm just going to change that speed because the speed is a little slow. So here are the delays. If I just change this one to 300 and this one to 100 and we try the game again, maybe that'll be a little more acceptable. So the game doesn't get a lot of testing when I'm porting it to new systems because I have to work quite quickly to keep my schedule up. That's a bit more like it. There we go. So there we go. The game's working at proper speeds, I think now. That's about right. Anyway, so what we're going to do today is we're going to go over the source code and we're going to discuss all of the sections that are new. We're not going to discuss the parts that are the same as in the Yquest series. That means the joystick reading and the screen plotting routine that calculates the memory addresses. We're going to discuss the bit that calculates the pixels, but the memory address calculation for a byte of the screen based on an XY coordinate is unchanged since Yquest and the simple series, so please see those if you need to know how that works. Of course, you can download the source code for today's example if you just want to use it, but if you need to know how that works, you'll need to watch those other videos because I don't want to discuss it again because I've been over it quite a few times now. Right, well, the game engine, as always, works on multiple systems. So we've got some variables here that configure it for this particular system. We've got the screen size settings here. We're using the smaller scale for the title screen. We're scaling it down by 50%. So we've got the screen width set to 20, which is designed for the handhelds usually, but it also works nicely on these narrower 162 pixel wide screens. And we've got 4 color definitions. Now 0 is black, and we can use up to 4 other colors this system because we're defining the color attributes for the entire screen to be the same. We've effectively only got 3 other colors, so we're defining color 4 as color 1 just to remap it. We've got our screen initialization here. This is all the same as before the simple series on Yquest, so please see one of those if you need to know about that. We're clearing the variables for the game here. I should have mentioned that. We're defining a kilobyte or so of data here. That's for our game variables. And then we're showing the main menu here, and this is all multi-platform code that we've covered in other lessons. So here's the start of the main loop. Now, if you remember, when I hold down fire, we will move faster, and the way that works is we have something known as the tick, which will be 1 or 0, and it alternates between frames. Now, in boost mode, we draw on every tick, and in normal mode, we draw on every other tick, and the CPU doesn't use boost mode. It's just a player thing to give the player some challenge of trying to catch up with the computer. So that's what that tick does, and then we're setting the delay speed. Now the boost mode, when it's enabled, has to update the counter in the corner of the screen, and the vector fonts aren't particularly fast, so we have to reduce the length of the delay in boost mode just to compensate for that. Now the disadvantage is they're not fast. The advantage is they work on all the systems and they allow for scaling, so I think overall they were worth having, but that is the disadvantage of them. They're slow. Right, now what we're doing next is we are checking for any key presses, and we're using the same joystick routine as Yquest, and we're seeing if any keys have been pressed, and if they haven't, then we're clearing something known as the key timeout. Now you remember I said if you press down a key you have to release it to keep turning, and that's what the key timeout does. So if the keys have been released, we're clearing that key timeout, and that means any future key presses during this delay will be processed. So that's what's happening there. Now there's our loop for the delay, and then we're actually looking at the key presses, and first we're checking that key timeout, and if it's still set because the key's never been released, we're not going to process any directions. Otherwise we're going to turn the boost off, which we do by writing a 1 to the boost variable. We write a 0 to the boost variable, you can see down here, if we need to turn the boost on. Now what we're doing next is we're loading 0 page entry IX, that's a defined pair of bytes there, with the address of the player's X acceleration. Now this is used by the set player direction function, which is in the multi-platform section. What we do, you see, is we check the directions and we see if left or right is pressed, and we decrease or increase the player direction, which can be one of the 4 directions, north, south, east, west kind of thing. And then what we're doing here is we are updating that with set player direction. What that does is it copies a template X and Y acceleration for that direction into the player's acceleration, and that's why we need to set that up here, and we don't ever see AX used in this section because it's that set player direction doing the work. And if left or right are pressed, we're setting the key timeout. Then we're checking if boost fire is pressed. If it is, we check if the boost counter is 0, and if it's not, then we can use boost. So we turn the boost on here. You'll notice there's no key timeout set for there because the boost needs to be held down. Now, the actual boosting is done by the handle player routine, and that does all of the other player collision detection, all the other stuff that's not related to this graphics system. It's related to the game itself, and that has to all be in the multi-platform code, and that's how we split the game up and we make it as portable as possible. And then there's the handle CPU routine here, which does the same basic stuff for the CPU, and then we've got a jump back up here to the main loop. There we go, that's the entire game loop there. So most of it's in the multi-platform code, which is the way it should be. Now, here's our graphics routine for PSET. So what this is going to do is it's going to take an X and Y position. Now on sim systems we need to go over 256, but on this one we don't. So what we're doing is we're using the B, 0 page entry marked as B for the X position and C as the Y position. And this is the same as the GetScreenPause function we wrote in the past, but this time we're working in pixels and not in bytes, and we're going to have to compensate for that. So the first thing we're doing is if we're checking if the value we've been given is negative. There are some cases where we use a negative value to position the boost text at the very, very far left of the screen, and so to avoid drawing off screen, we're just checking if we're getting a value that doesn't quite look right there. So that's what we're doing there. Here in D is the color we want to draw, which will be 0 to 3. And then we're using a function called getPixelMask. Now this does most of the work for us, and we'll see it in a moment. It calculates the HL memory address of the byte of the screen we want to change, and it gives us 2 masks. It gives us D, which is the background mask, and this is to keep the pixels that we don't want to change, because a byte of the screen in the mode we're using, there will be 4 pixels, each of which uses 2 bits, and those 2 bits are of the course of the color. But we will need to keep 3 of them the same and just change 1 of them. So the D entry in 0 page D here, this is the mask to keep the background pixels, and the E mask is the mask to change the pixel that we want to change. So that's calculating all those, and it's also calculating HL to point to the byte that we should be messing with to change the pixel we want, and the pixel of course defined by XY position in BC. So that's doing all that for us, and we'll see it in a moment. Now that's given us a mask for the pixel, but it's in the wrong color. So we've got another function called getColorMaskNumber, which will get the mask for the color, and it will return a byte where all 4 pixels are the color that we specified. If we AND that mask with E, which is the pixel we want to change, the result, which we store back in E, will be the pixel we want to change in the color we want to change it to, and that's what we want. So we got that now. Now all we do is we load in the byte from the screen. We clear the pixel that we want to change, keeping the 3 pixels we don't, or in the new pixel for that, and then we store it straight back to the screen, and that does the work of the PSET. Of course, it doesn't do the work of calculating all the stuff here, which we're going to see just now. So here is the routine that's actually calculating the masks and the screen position. So we've got this GetScreenPause here. Now this is identical to the version we used in Yquest. Now the difference is, of course, this works in screen bytes horizontally, and we're working in pixels, and there's 4 pixels per byte. So what we're doing here is we're doing some bit shifts to B to take away the pixels and convert that to a byte coordinate. Now that's what we're doing there. And then when we use GetScreenPause, that will indeed calculate the byte position and give the resulting memory address of the byte we want to change. What we're doing next is we are getting the remaining 2 bits, which will be the pixel position within the byte, and then we're using a lookup table to give us a mask for that pixel. We store that in E. We then flip all the bits, and that will give us the background mask, which is not a background mask. It's a terrible typo there. So a background mask, and we store that in D. And the pixel bit lookup, well, you can see that just here. So the leftmost pixel is these 2 bits here, these 2 here for the next one, these 2 here, and then the right one, these 2 here. So nice normal layout, I would call that, not like the CPC and weird ones like that. Now that's how we get the pixels. When we want the colors, again, we're using a lookup table here, nice and easy. This is a great easy thing to port to other systems. There are probably other ways of doing things that may be faster for one specific system, but this is nice and easy to port to different graphics hardware. So again, we're taking 2 bits here. This time this is a color from 0 to 3, and we're looking up that color here, and we're returning a byte with all 4 pixels set to that color. So color 0, color 1, color 2, or color 3 here. And that's how we're doing things. So that's the pixel masking function, which is doing the dirty work of calculating how we're going to deal with a pixel on the screen. And it works pretty well, really. It works pretty well indeed. Now, once we've got that, we can basically convert that into a point routine, and that's what we've done here. So this is going to read a pixel off the screen, and this is how we detect if the player has died, or if the CPU has died, of course, as well. Basically, almost identical to before. Get pixel mask once again, which is calculating the screen byte address and also the masks for the pixel we're looking at. This time we don't need the background, so we just read in from the screen, mask with the mask for the pixel we were looking at, and that will now give us a pixel, but it won't give us a color from 0 to 3. Now, truth be told, it doesn't matter for Yquest because black is safe and everything else kills us. But if we wanted to get a bit clever and had power-ups that were different colors or something clever or weird like that, or did up points for hitting the background and more and killing you instantly for hitting the CPU or something, then we'd need to know the exact color. And the way I'm doing it, and it's not necessarily the best way, but again, it's a way that's easy to port to other systems, which is often my priority. What I'm doing is I'm converting that pixel read from the screen back into something that I can compare to the color lookup that I mentioned before, where all 4 pixels within the byte are the same color. So what I'm doing is I've got this byte to color mask function, which will convert a single pixel into a byte that's full of that pixel. And so we're taking the position here, shifting to the far right, and then we're filling in all of the pixels with that color. And then we are comparing using this color lookup here. And that will give us a number from 0 to 3. And as I say, this is excessive, to be honest, for this system, because the pixels are laid out nice and neatly within the byte. But on systems like the Amstrad CPC in mode 0, they are definitely not. And so, as I say, this is kind of a thing that's very multi-platform. But this byte to color mask function can also be helpful for other things, because if you are shifting an image by 1 pixel, for example, you will need to read in each of those pixels and then convert them to a color and then convert them back into a new pixel position for the new screen location. I did do an example of that on the Amstrad CPC, and in that case again I used this byte to color mask function. So there may be cases where it's helpful, even though, to be honest, it's probably just slowing things down here, although it's not a priority for this game. The point command's only used twice per well, almost twice, I think maybe 3 times per execution, because it's used for the player to see if the player's died, it's used for the CPU to see if the CPU's died, and then it's used maybe a few times for the CPU AI to decide which way to turn. So very rare, and speed wasn't a priority. But if it was a priority, you'd want to get away from this lookup table and just convert the data within the pixel into a number from 0 to 3 on this system, because the bits are logically organized anyway. Now, this game uses just 4 colors, 0 to 3. It doesn't use the color attributes on the Commodore 64. I kind of consider 4 colors to be the ideal, if you will. 5 would be better, but 4 is perfectly fine. On systems with just 2 colors, like the Spectrum, I do use the color attributes, but on this one I haven't. So our clear screen is doing all of the work of clearing the byte data of the bitmap screen, and also setting the color attributes. So here is the color attributes being defined. So we've got cyan and magenta here, and we've got the green here. And if you wanted to change the colors, this is where you'd effectively do it. Now you could, if you wanted to be clever, you could make your PSET routine and calculate the screen position and set a color attribute accordingly if you wanted. I did do that on the 2 color systems, but as I say, that's beyond the scope of what I'm doing here. And then we've got GetScreenPause, and again, as I say, this is calculating a byte position of the screen for the XY position specified, and that was covered in Yquest. And GetCommentPause actually isn't used; it shouldn't be there, but it's there anyway as a bonus, maybe, or maybe just because I've got a very bad memory. I'll leave that to your judgment. Anyway, there we go. So that's the example we're looking at today. As always, you can go to my website and you can download it and you can compile it, and maybe you can get some use out of it, or maybe you can make it better and laugh at me. I don't care what you do. I hope you have a lot of fun with it, whatever you decide to do with it. Anyway, if you've liked this video, if you hit the like button, that will help me out, because YouTube recommends videos based on likes. And if you subscribe, then I'll probably think of doing some more Commodore 64 stuff in the future, so that would help out as well. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.